Hi Year 11, today's video looks at the pigeonhole principle. This is the last principle that we're looking in our first section of combinatorics, and it's probably something that you've not heard of before because it's kind of relatively new to the syllabus. The pigeonhole principle actually started by looking at pigeons. So here we've got 5 pigeons and we've got 4 pigeonholes. So say each of those pigeons went into a pigeonhole. So we've got 4 holes, so they would be full, but there'd be 1 pigeon left over. And that last remaining pigeon still needs to go into one of those holes. So it needs to go into any one of those 4 holes. So what we're going to have is one of those holes is going to have 2 pigeons in it. So we say that at least one pigeonhole will have at least 2 pigeons in it. And that's assuming they're all distributed evenly. Otherwise, we might have another hole that has multiple pigeons in it. So I've written all over our notes here a little bit, but basically what the principle is saying is we have 11 pigeons and they fly into 10 pigeonholes, and I've named N as my pigeons and D as my pigeonholes because I'll show you a little formula in a moment. But if those 10 are going into 11 are going into 10 pigeonholes, there'll be at least one pigeonhole with at least 2 pigeons in it, and that's pretty much common sense if you think about what's happening there. If 31 pigeons fly into 10 pigeonholes, there will be at least one pigeonhole with at least 4 pigeons in it. And thinking like that, how we would do that, or think about that, is I'd be dividing my 31 here, I'll just do it up here, by my 10, and that's going to give me 3.1. So we can't have 0.1 of a pigeon. So in this principle, and it sounds a bit funny, we're not chopping pigeons up, we're having whole pigeons. So that would say that there's 3 pigeons in each pigeonhole. And this 0.1 is saying, well, hey, that's going to round up to 4. So there's going to be at least one that's got 4 pigeons in it. So looking at the last bit here, it says if there are 10 pigeonholes, then the least number of pigeons that will guarantee that there is at least one pigeon hole that has at least 8 pigeons is 71. So what we're saying is it's going to take 7 pigeons in those 10 pigeonholes to get them all filled. So if we've got 7 in each of those 10 pigeonholes, we've got 70 pigeons. But what it says there, that there is at least one pigeonhole with at least 8 pigeons in. So we're assuming that they're distributed evenly along. One of those 10 pigeonholes, if it's got an extra one in, it's going to have 18 instead of that 7. So we're going to add one more to it. So we're going to end up with 71. So they're kind of logical if you think of them like that. Now let's formalize that principle, and we're kind of, when we're formalizing this principle, thinking back to our polynomial topic when we've got remainders, and if the pigeons fit perfectly into the pigeonholes, we're not going to have a remainder, and if they don't fit perfectly in, we're going to have a remainder, and that remainder pigeon has to go somewhere else. So let's think of it still as pigeons. So suppose that N pigeons fly into D pigeonholes. Performing the division, we get N equals QD. So D is our pigeonholes. Q is how many are in each pigeonhole. And we've got some remainder. And that remainder could be any value. It could be nothing, but it could be up to one value less than that D there. Otherwise, it would fit in perfectly. So we just have to think back to what we did in polynomials there. So if we've got no remainder, then basically our N is going to divide neatly by our D, and we're going to get Q, and we're going to have no remainder. And that will give us how many pigeons are in each hole. But if we've got the remainder being greater than 0, then there must be at least one pigeonhole with Q plus 1 pigeon. So that's that leftover pigeon. So that those leftover pigeons, and there might be more than one leftover pigeon, still need to be dispersed into those pigeonholes, and some of them are going to have an extra one in there. That's what that is telling us. Okay, the bottom part says the least number of pigeons that will guarantee that there is at least one pigeonhole with at least Q plus 1 pigeons is QD plus 1. Now, I think that bottom one there, probably best not to memorize that, but we'll think of the questions logically. Now, we've talked about pigeons so far. Most these questions that we're going to have a look at with this topic are not going to be about pigeons, but if you think of it in terms of pigeons, and I generally allocate one of the numbers to be the pigeons and one to be the pigeonhole to work it out, and then it can often be a little bit easier for us. Okay, let's have a look at that first example. The first example says an office block has 15 offices to choose from. So in this case, I'm calling my offices the pigeonholes. So I've got 15 pigeonholes to fill. How many people are needed to ensure one office has 2 people? Okay, so if one office has 2 people, we want to think first of all, well, there's 15 offices or 15 pigeonholes, and we're going to put one person in each of those offices or pigeonholes. So we're going to have 15 of those filled. One of those is going to have 2 people. So I need to pop an extra person into one of those. So I'm going to get an extra than 15. So I'm going to have 15 plus 1, which is 16. So that's as easy as that's going to be for us. That's quite simple. Part B, how many people are needed to ensure one office has 5 people in it? Now the key there is that only one office has 5 people. So the other offices are going to all have 4. So the 15 offices that we've got are going to have 4 people. So 15 times 4 is 60. And then one of those offices is going to have 5 people in it. So we're going to add 1 to that 60 and we're going to get 61. So we need 61 people for that question. Okay, next example. 61 people sit at a restaurant. There are 15 tables. So you can see here, pigeonhole wise, 15 tables are our pigeonholes and there's 61 pigeons or people to fill those holes. So we've got in the same context, but we're looking at a table. There's 61 people sit at a restaurant. There are 15 tables and the guests are distributed evenly. Prove that there must be at least one table with at least 5 guests. Okay, there's 2 ways to think of it. Now, if you had a look at the Atomi video that I showed you, what they do in there is get our 61, divide by 15, and we get 4.1. Now, we can't have part pigeons, we can't have part people. So we're saying that, well, there's 4 people at each table, but we're going to round up to 5, so we're going to have one that's going to have 5 in there. Thinking of our question above, or our formula above, how do I write 61 in terms of a multiple of 15 and then a remainder? So I've written 61 as 15 tables times 4 people. 15 times 4 is 60 plus 1. So that tells us that 15 tables have 4 people at them, but there's this one extra person that needs to go to one table, and that will be getting us that value of 4 plus 1 at that table, so we'll have 5 people at that table. And either way, you'll be able to work it out and think in that case. But if you were doing this method of division, you'd need to make sure that you round up to get your 5, because we don't have part people. Let's look at the last example here. The last example, okay. Mary has 30 distinct hair ribbons, so they're all different. Every day, including the weekend, so we've got 7 days, she selects a ribbon at random to wear. How many successive dates are needed to guarantee there is at least one day of the week on which she has wore the same hair ribbon on 6 occasions? So it's only one day of the week. I'll underline that bit there, that she's worn 6. So we're going to assume that she must wear a ribbon on 5 occasions on each of the days, and then there'll be one where we get the 6 from. So if we look over here, the working is 30 hair ribbons. We're going to wear them over 7 days, and we're going to have them 5 per day, and that will get us the 5, but we want one of those days of the week to have had 6 ribbon wears or ribbons, so we're going to add that 1 on top of that. And that will give us a value of 1,051 dates.